Welcome to iLectureOnline. In this example, we're going to see a very important connection between the center of mass of several objects colliding and the conservation of momentum. We can best illustrate it through this example right here. Let's say that we have two objects. They're going to be of different mass. This is mass m and this is mass 2m, so this has twice the mass of this object. This object is moving to the right at 8 meters per second. This object is moving to the left at 2 meters per second. Notice at t equals 0, they're 20 meters apart. If we calculate at this moment the location of the center of mass, we can do this as follows. It's the mass of the left object times its location plus the mass of the right object times its location divided by the sum of the masses, which puts the center mass of 13 1/3 meters from the origin, right there. 1 second later, the two objects have moved towards one another. Now they're only 10 meters apart. This one is still moving to the right at 8 meters per second. This one is still moving to the left at 2 meters per second. But now the center mass has moved to the right. Again, when we calculate the center mass, it's mass times position plus mass times position divided by the total mass. It's now 14 2/3 meters from the origin. In other words, the delta distance for the center mass is equal to, that would be 4/3 of a meter in 1 second. In other words, the velocity of the center mass is equal to 4/3 meters per second. It's moving to the right at a rate of 4/3 meters per second. Now, what happens to that as the collision proceeds? 1 second later, the two objects are not colliding with one another. They're now at the point 16 meters to the right of the origin, which of course means that the center mass of the two objects is at 16 meters. Again, notice it is 4/3 of a meter to the right of where it was a second before. But what happens after the collision? Well, assuming that the large object is now, after the collision, moving to the right at 2 meters per second, we had them to calculate what the velocity final would be for the small object, and it turns out when we work that out, it is 0 meters per second. So the small object bounces against the large object goes to the right at 2 meters per second, the small object stays in place to satisfy the conservation of momentum. Well, where is the center of mass 1 second later? 1 second later, the large object now would be at 18 meters, from 16 to 18, because it's moving at 2 meters per second. The small object will remain at 16 meters. So this is at 16. The large object is now at 18 meters. And if we calculate the center mass, again, it's 4/3 of a meter to the right of where it was the second before. So again, the change of distance of the center mass in the next second after the collision is again 4/3 of a meter. That means that the movement of the center mass, and of course that's kind of an interesting thing because it's not an object, it's simply a location of the center mass of a group of objects. In this case, the group is two objects that are colliding with one another, but through the collision, before, during, and after the collision, the center of mass of the two objects continues to move at a constant speed, unchanged due to the collision. And it doesn't really matter how much of the energy is conserved in the collision. If it's 0 energy conserved or 100% of the energy conserved, the center mass will continue to move at a constant speed, unchanged during the collision, before, during, and after, through the entire process of the collision. And that's the key to understanding the conservation of momentum, is that the center of the mass of objects is unchanged in its change. In other words, if it's staying put, if for some reason there's two objects of the same speed, same mass, colliding with one another and then bouncing back off at the same speed in the opposite direction, the center mass will remain in the same location. But if it's a collision where the objects have different masses and different speeds, so that the center of mass will move during the process, before, during, and after the collision, that constant change will not change. You can see that the difference of location of the center mass continues to change by 4/3 of a meter throughout the entire process. So that's absolutely key to understanding conservation of momentum, and it'll be key to understand the coefficient of restitution, which we'll get back to in just a few more videos after we understand this property a little bit better. And that's how it's done.